All right, let's have a look at Newton's second law here. Okay, so with Newton's first law, we said that's the situation in which all the forces are balanced, the net force is zero. Newton's second law deals with all the situations in which the net force is not zero. So there is a net force, and as a result, the object is going to change velocity, that is, accelerate, okay, from wherever it is, right? So, okay, essentially, Newton's second law tells us the relationship between force, mass, and acceleration through this formula here. Okay, F equals m times a. Nice, easy formula, right? Three variables is like v equals d over t, except it's never that simple. Okay, remember that the net force is also, it's calculated in two ways. Okay, I can calculate F net by going mass times acceleration. I can do that, but it is also the vector sum of all forces. Okay? And more often than not, we have to find that vector sum in order to get the net force so we can calculate like the acceleration or something like that. Okay? So it's never as easy as just F equals m times a. Right? This is why we draw the free body diagram and then why we draw a vector diagram after that. Now, do you always have to draw a vector diagram? No. Okay? If you've simply got collinear forces, then don't bother drawing a vector diagram. Okay? There's no point in doing that if you can just add or subtract them all. But if they're angled, then you're going to have to do trigonometry and vector component addition like in the last unit there. Okay, so understand how force and mass influence change in velocity. We talked about that a little bit ago when we were talking about how the acceleration of an object, okay, is related through this manipulation of the formula. Okay, the force can determine the acceleration. According to this, the bigger the force, the bigger the acceleration. That sort of makes sense. The harder you push something, the more it's going to accelerate. Okay, and it's inversely proportional to the mass. The bigger the mass, the smaller the acceleration will be, and that would make sense. Okay, if I push, a kid on a tricycle, I can accelerate them fairly well. But if I try that same force on a pickup truck, I don't produce the same change in velocity because I'm exerting the same force on a much larger mass. Everybody follow there? Yes? Okay, we got to understand kind of that relationship. Okay, bigger the force, bigger the acceleration, and that's linear. If I double the force, I double the acceleration. Okay, for mass, it's the opposite. If I double the mass, I'll have how much acceleration? Okay, if this number is twice as large, this number will be half. Okay, so it's inversely linear. Okay, this one's linear, this one's inversely linear. All right, so the second law deals with what happens when there is a net force acting on an object. Okay, again, if we go back to the hockey puck example, now we're talking about when the stick is in contact with the hockey puck. Okay, the force is being applied, it's not balanced. As a result, the puck changes velocity. Okay, and the acceleration, okay, the cause of the acceleration is the force the stick applies. So it only accelerates as long as it is in contact with the stick or as long as the force is being applied. Okay? A lot of sports science depends on Newton's second law. Okay? For example, the design of hockey sticks now is far different from when I was a kid. Okay? When I was a kid, a hockey stick was a chunk of tree. Okay? It was just wood. You went and you bought a stick and it was made out of wood and that was it. Okay? That was the only kind of stick you could get. Now you can get composite sticks, graphite sticks. They're made out of all kinds of different materials, and those materials are superior in many ways to just normal wood. Okay? Is wood somewhat flexible? Yeah, it's somewhat flexible. An old wooden stick will flex a little bit, but it doesn't flex anything like the new composite sticks do. Okay? Well, what that does is it increases the distance over which I can exert the force. The longer I can exert the force for, the longer the puck accelerates, and thus the faster I can shoot. Okay? The puck will go faster because I exerted the force and accelerated the puck longer. Everybody follow me there? Okay? So if we're looking at kind of an arc here, okay, like an old wooden stick, okay, may have had an arc like this over which it could exert a force because it didn't flex very much, right? But a modern stick because it can flex, okay, can exert a force over a much longer distance. Okay? Now, there's a drawback. What often happens to composite sticks? Yeah, they snap, right? Like if you ever watch like a professional hockey game, like 2 or 3 sticks a game at least, okay, get snapped. Somebody's winding up for a big slap shot and the stick just explodes. Okay? There's a cost for that added flexibility, and that is that they are a bit more fragile, okay, in terms of if they take an impact, like somebody, smacks your stick with their stick, it puts a notch in it, whatever, okay, it can likely snap along that same spot. All right, so does that sort of make sense there? As long as I'm in contact with the stick or with the puck, I can accelerate the puck. Okay. Other sports that do this, okay, golf. Okay, golf has like more flexible shafts on the club, okay, enabling us to get more time in contact with the ball. The ball is made differently now. Okay. 30 years ago, the ball was hard as a rock. Okay, it was just very, very rigid. Now they compress and they actually flatten against the face of the club, meaning they stay against the face of the club a little bit longer, allowing you to be in contact with them and accelerate them at a greater speed. The clubs are lighter, which means you can swing them harder, faster, not necessarily harder, but faster, okay, because they're lighter. Okay, all of these things are taking advantage of Newton's second law. They're allowing that force to be exerted over a greater distance. Okay. All right, so as long as the force acts, the velocity increases. Okay, that's the key thing to remember about Newton's second law. Okay, the acceleration only occurs as long as the force is being exerted. Once the force is gone, we're back to Newton's first law. Okay, and remember also that the relationship is directly proportional. That is linear. 2 times the force is 2 times the acceleration. Okay. And the net force, I'm going to change that to net force. Okay, the net force and the acceleration have the same vector. All right, so if I had 2 forces acting, okay, one forward and one backward, okay, my net force is, I shouldn't use blue on a blue background, okay, is this direction here. All right, that's the direction of the net force. That's the direction that the object is going to accelerate. Okay, I can't have a net force east and an acceleration that's anything other than east. Okay, they always have to be the same direction. Okay, so lots of times several forces act on an object at the same time. This is probably the hardest part of Newton's second law, is identifying all the forces acting on an object and showing them in both the vector diagram and the free body diagram. So what we see here is another example of a free body diagram. I've drawn the object, okay, and I'm showing the 2 forces acting on it, force 1 and force 2. According to this diagram here, it looks like force 1 is a little bit bigger than force 2. So we have a net force that's going to be to the right. Okay, and the object will accelerate that direction. Okay, so remember, okay, that the net force is the vector sum of all the forces acting on the object. Okay, so there's always 2 ways to calculate net force: mass times acceleration and the vector sum of all the forces. And in most questions, you'll have to use both. Okay, so this diagram kind of illustrates again that relationship here. Okay, if we're talking about Newton's second law, and I have situation A, where I have this guy with a golf club, okay, and he's hitting the golf ball with it, okay, the force that he can exert is determined by his strength and technique. And we'll say it's always exactly the same. Okay, so if he swings as hard as he can, this is the force that he can exert. All right, he is exerting that force on a very small mass, a golf ball. And as a result, he will produce a very large acceleration, okay, because the mass is so very, very small. If for some reason we decided to line him up here where he would instead hit a truck, for whatever reason, okay, with his golf club, then the situation changes. He still can swing this hard. The force hasn't changed. But now He's exerting that force on an incredible mass, and as a result will produce a very small acceleration. Okay? At this point, most people point out that the truck isn't going to move, which isn't true. Okay? If it was sitting on perfectly frictionless ice, it would in fact slide forward. Okay? If it was on perfectly frictionless ice, it would slide forward as a result of being struck by the golf club. Since there's no such thing as perfectly frictionless ice, the truck as a whole does not move. That doesn't mean the particles that make up the truck don't move. They do. Okay? If I'm standing at the front of the truck and I have my hand on the front of the truck, do I know when he hits the truck? Yeah, even if I've got my noise canceling headphones on, I still know when he hits the truck because I feel the vibration pass through the truck, which means he has caused every particle, that is all the mass of the truck, to move. He just hasn't got it all to move in the same direction at the same time. Okay, that still counts as an acceleration. Okay, does that sort of make sense to everybody? Okay, all right. Okay, so when a net force acts on an object of whatever mass, the acceleration that results is directly proportional to the force. So this is Newton's second law written out in words. Okay, so that's what it would look like written out, or like a definition of Newton's second law. Okay, written out mathematically, okay, F net equals mass times acceleration, which we've also said also equals the vector sum of all forces. Now, we've been saying so far in this unit always that the units for force are newtons, and that's what we use. Okay, we use the term newtons, but that's not the fundamental units for force. Okay, if we look at this formula here, we're multiplying mass by acceleration. Mass is always in kilograms, and we're multiplying that by acceleration, which is meters per second squared. So a newton is a kilogram meter per second squared. Okay? Those are the fundamental units for a newton, a kilogram meter per second squared. Newton's just easier. Okay? You kind of pay homage to all the stuff that Newton contributed to physics, okay, by naming the unit for force after him. I would assume that shortly there will be some unit called a Hawking. Okay? I would assume. All right, does that make sense to everybody so far? All right, so free body diagrams, okay, like we said, they always show the forces as though they act from the center of the object, okay? We never draw a free body diagram this way, okay? We always show the forces as though they act from the center of the mass that we are dealing with. All right, so in a case of an object that's just sitting on a table, like my coffee cup there sitting on the desk, okay, the free body diagram of that would be gravity is pulling it into the desk, and the desk is reacting by pushing back up, and thus my cup doesn't go anywhere. It just sits there on the desk because those two forces offset each other. Okay. Everyone all right with that idea of the reactive force? Sometimes people kind of have a trouble envisioning that. Not necessarily fall over, because the only way to make it fall over would be to exert a force probably from the side. If the force downwards was greater, then it would fall, right? It would go through, right? But they're balanced. As an example, if I want to jump, okay, I don't push up. Which way do you push? Okay? If I want to jump, I bend my knees and I push down. I push against the floor. I make the floor push harder back. Okay, so because I increase the force down, the floor has to push harder against me, and I fly off the floor. Okay, so in order to jump, I actually make the floor push harder than gravity is pulling, and as a result, I fly off the floor. Okay, seems weird, okay, but that's kind of how reactive force works. Okay, there's always a reactive force. If there wasn't, things would be really, really weird. That's why we usually call it the normal force. Things wouldn't be normal without that reactive normal force. Yeah. Okay. I mean, if I push down on this cup, okay, so now gravity is pulling down, I'm pushing down, and the desk has to push harder. Right? In this situation, the desk only has to push equal to gravity. Now it has to push even harder. Okay? And I can feel that against my hand. I can feel the cup pushing against me. Okay? It's why you can't sit forever. Okay? Your butt gets sore because the chair is always pushing on it. Okay? There's always that reactive force. If you're standing for a long time, your feet get sore because there's always a force pushing against your feet. It's not gravity that makes you tired. It's the force you work against as a result. All right, let's try this one. This is a simple Newton's second law problem, like about as basic as they would ever get. All right, I have two people pushing a stalled car, okay? Because back in the day, when more cars had manuals, you could actually start a car by pushing it. Yeah, you can't do that with an automatic. It's unfortunate, okay? But we weren't just worried about dead batteries back in the day because we could just know if we push it, okay, throw it in second, pop the clutch, it would start. Okay, it's really cool. All right, so we got these two people who are pushing this car, okay, to wherever. So one person is pushing with 275 newtons of force, one pushing with 395 newtons worth of force, and there's friction opposing with 560 newtons. Right? Those are the three forces involved in pushing this car. Right? So just quickly looking at this, there's more force forward than there is backward. Agreed? Okay, so the car is going to accelerate forwards. We have to calculate what is its acceleration going to be. So the first thing I'm going to do is draw a free body diagram of this situation. They tell me the car has a mass of 1,850 kilograms. So I draw a box, which is great for me because I can't draw. Everything is just a box, okay? And it's 1,850 kilograms. Now I put the forces on that diagram, okay? We say that we make them kind of looking as though they come from the center. So I'm going to have my 275. Looks like a 9. So I have my 275 Newton force. And I have the other force here, which was 395 newtons. So there's my two forward forces. Okay, and I have a force backwards of 560 newtons, roughly to scale. Okay, do I need to draw a vector diagram of those forces? I mean, I could, but they're collinear. Is there any point to drawing them tail to head? They're just going to be right over top of each other anyway. Okay, I can just figure out what the vector sum of these forces would be. Okay, so I'm going to go F net equals positive 275 plus positive 395 plus negative 560. Okay, I'm finding the vector sum of those forces. All right, because I can't find F net using M times A. I don't know what A is. That's what I'm being asked to find. Okay, so remember how I said you're going to use both ways in basically every question? I'm using the sum of all forces to get F net, and then I'll use that to solve for the acceleration. Happens a lot. Okay, so we got 275 plus 395 minus 560. All right, so my net force is 110 newtons forward. All right, now I know 110 newtons equals mass times acceleration, and I know what mass is. Okay, so acceleration will be 110 newtons divided by 1,850 kilograms. Whoop. All right, is that a very big acceleration? It's like 6 centimeters per second squared. Okay. It's not much, but if you kept pushing, you would keep accelerating. So you'd keep going faster and faster. If you kept pushing for, 30 seconds, you'd get the car moving. Okay. It would be moving at a reasonable rate of speed. Okay. So we're going to get here essentially 6.0 times 10 to the minus 2 meters per second squared. Okay, not very much. Okay, everybody follow me on that. And then we would have to put a vector on that. It would either be positive or forwards, okay, or something like that. Okay, that's about as simple, okay, as those questions will get. We'll spend probably right up till Easter on Newton's second law. Okay, it's a big concept, and there are an unthinkable number of applications for it. So we need to go over as many applications and situations in which it applies as possible. So we will spend quite a bit of time on it. It is the bulk of this unit. Okay, I know right now you're thinking, really, I could spend 3 weeks or 2.5 weeks on F equals M times A. Yes, okay, because it's not just F equals M times A, it's that whole vector sum of all forces thing. You got to be able to look at any given situation, visualize the forces, what direction they're going, how they contribute to all of that. Okay, so there's a lot of stuff that we have to kind of experience so that we have kind of that level of experience to approach more difficult problems. All right. So in this unit, guys, we will have a few labs. Okay, we'll have Newton's second law lab. We'll also have a lab with work and energy, conservation of energy. Right, so there'll be probably 3, maybe 4 labs, depending on how it goes. Probably 4 actually, because we'll have one on friction as well. And then we'll have a couple of little kind of in-class things. A Newton's second law assignment, like your vector assignment. Okay, so there'll be one of those in there. So things like that. So expect that within this unit, which will run probably till mid to late April, because we have that week off for Easter in there, okay, that you'll have several things coming in. So expect you'll probably be handing in something every week during this unit, which is pretty much par for the course. That's what you've done thus far anyway. Okay, you do not have a quiz tomorrow. Okay, haven't taught you enough to quiz you on anything yet, right? But you will have one on Tuesday, right? So you get a little break today. I know you don't have a quiz tomorrow, but you will have one on the Tuesday. It's okay. I'm awake enough for both of us. Okay.